Hi everyone, welcome to week 7. I think it's week 7. I hope it's week 7. I kind of combined some weeks and I think there's 3 more to go after this, so that will make it week 7. This is the pointy maths end of things with stoichiometry, stoichiometry being measuring the efficiency of a process. Industrial chemistry, making things out of chemicals. And I'll focus on one particular process and set of chemicals through the whole thing. So if I mix one of this and one of that, I should get 2 of this, theoretically speaking. Stoichiometry is the study of theoretically how much should I get when I mix A and B, and then looking at why you didn't get what you theoretically should have got. So there's, according to the maths, this is how much I should have, but when I've actually made this product, I only have this much. Why is that? And that is what stoichiometry is about. There's Jacob. I'm going to minimize all these so I can't see you, and no one can see you. So, efficiency, so we make the green liquid. How efficient a synthetic pathway is. So a synthetic pathway is just creating a pathway to make a product that pathway doesn't exist in nature. And the wastes that are produced. So the ultimate goal is to produce more of the product and less of the waste. From an industrial point of view, this makes perfect sense. The less waste there is, the more product there is, the more money you make. So the theoretical yield is, if mathematically speaking, if I add this and this, then I should get this. So you get a 100% conversion rate of the reactants into the product. So if you add sodium and chlorine together, then you should get an equal amount of sodium and chlorine. Sodium chloride, sorry. So these stoichiometric mole ratios, and I'll explain them as we go through. So the actual yield is what we actually got. So some numbers up. Really large, clean off my whiteboard before I start these, but there you can see how smart I am. So the theoretical yield is 1 plus 1 equals 2. This is the theoretical yield. So 1 plus 1 equals 2. If I run this process and I get 1 plus 1 equals 0.5. And this happens because the real world is not maths. The real world has other factors. And this is our actual yield. So we put that into grams, and we display this actual yield as a percentage. So we only got 25% of the reactants as products. And we really should be getting closer to 75%. And we use this to determine whether or not, I'll just stop sharing so you can see the whiteboard. We use this to determine whether or not there are efficiency issues. If the math says you should get 2 grams, but you're only getting 25% of that, then something is off. So it may be the heat, the pressure, the volume, how pure your reactants are. So if there's contaminants in your reactants, then the reaction won't happen as it should. So that is what we mean by the theoretical yield and the actual yield. And if you're looking at the slide, I'm just going to keep sharing the whiteboard here. So we have this concept of the equilibrium. Once a reaction reaches a certain point, the reaction, so product 1 plus reactant 1 plus reactant 2 to reactant, that's a product 1. So we add reactant 1 and 2 and we get product 1. At a certain point, when you get enough of this product, the reaction happens in reverse. So this product then starts being broken back into the reaction here. And we don't want to get to this point because obviously we're trying to produce this. So we will run this reaction until we hit this equilibrium. So once a certain amount of this is produced, there's too much of it in the system, so the system then sends it back and breaks it down into this, so everything is even and equal. So the percentage yield that I did there, 25%. Percentage yield so our actual yield was 0.5 grams divided by what we should have got gives us, well, it would give us 0.25, which is 25%. That's how we calculate the percentage yield. You'll get a question and it will tell you this one. You have to calculate this and then you determine this. So this concept of trying to figure out how much of the product we have. Okay, here's our question. So 30 grams of propane 2-ol, don't worry too much about it if you don't know what these are. Is mixed with potassium dichromate and we get 20 grams. So our theoretical yield is 30, is the actual yield over the theory. Now let's remember that. So 30 grams of propane 2-ol is oxidized to make propanone and we get 20 grams. So we need to calculate the percentage yield. So the actual yield is 20 grams. the actual yield. We know that from the question because we have here the propanone distilled from the reaction mixture had a mass of 20 grams. And now we calculate the theoretical yield using stoichiometry. This is about as maths heavy as high school chemistry gets. It's not hugely complicated. It's just long and has lots of steps. So we calculate this. Following along on the slides. I'll stop sharing, so if you're following along on the slides, that will help. 20 grams is the actual yield. Theoretical yield equals, we don't know yet. So we need to calculate what's called the stoichiometric ratios. Now I've got one that I'm going to go through on the whiteboard that is a bit more complicated but a bit simpler at the same time. So 1 mole to 1 mole. So 1 propanol will make 1 propanone. So it's a 1-to-1, 1 product to 1 reactant. And you can see that on the slide, although I don't know if I actually sent this out to them. So once we know the ratio, so it's basically 1, same as we have 1 mole of propanol to 1 mole of propanol, or 1 molecule of each. And I'll go through a simpler process with this on the whiteboard in one go. So what we have to do is we have to calculate the molecular mass. So how much does 1 molecule of propanol weigh? And we do that, if you look at the periodic table, you'll see the atomic mass units. So find, if you're working along, atomic mass units of carbon, hydrogen, and oxygen. That little AMU button. So propanol, and usually in a calculation like this, the propanol, which is the reactant, has 3 carbon atoms, 8 hydrogen, and 1 oxygen. So we now need to know the AMU of carbon, so the atomic mass unit, which you can find on the periodic table. So I'll give you hydrogen, it's 1.008. The reason we're doing this, I'll get rid of that to avoid any confusion, is that when we're talking about how much of something there is, we don't use grams. Don't use grams, we use the mole. And if you look at the atomic mass unit, it is how many grams of something there is per mole. So hydrogen is 1.008. We move on to the next slide. So that equals 8.064. Carbon 12.011. Oxygen, I'm using 3 significant figures. 15.999. This equals, and this will become, I hope this makes a lot more sense in the next calculation that I run. So it has a molar mass of 60.1 grams per mole. So every time we have 60 grams propan-2-ol, we have 1 mole. And if we remember back a few weeks, 1 mole equals 6 times 10 to the power of 23 atoms or molecules. So we know that originally we started with 30 grams of this propan-2-ol. 30 grams. So we need to convert that into moles. So we would do 6.1. So we would have half a mole. Which means, so when we're talking about grams, that is not an amount of something. That is just how much it weighs. Moles is how many of them are there. That sounds very challenging. So we started with 6.022 times 10 to the power of 11.5 propan-2-ol molecules. So a little individual. We don't want to know how much that weighs. We want to know how many individual of these guys are. So we know we started off with half a mole of propan-2-ol because we have 30 grams, and for every 60 grams we have a mole. So we have half a mole of propan-2-ol. This is probably going to go into 2 sessions. So we have 30 grams of propan-2-ol or 0.500 moles. Grams tells us its mass, how much it weighs. This tells us how many of these molecules there are. In chemistry, in the industry, you don't care how much it weighs. It doesn't tell you much. You need to know how many there are. So remember, 1 plus 1 should equal 2. And we know that when we have one of these propan-2-ol, we get 1 propanone. So 1 to 1. The molar mass of propanone. So the molar mass of propan-2-ol is 60. Molar mass of propanone is 58.09 grams per mole. So we go, okay, half a mole, $58. So if 1 mole of this produces 1 mole of this, and we started off with 0.500 moles, or half a mole of this, then we can only produce half a mole of this. So we times this mass by 0.5. So this equals 29.05 grams. So this is our theoretical yield. Our actual yield was 20 grams. So we've missed the mark then. In order to determine theoretical yield, we divide by each other and times by 100. So we only got a percentage yield of 68.85. Now I'm going to do this on the board in a different equation, a simpler one that hopefully I've been teaching for many years, but I do it all out of my head. So I just wanted to show you on slides so you can see it. I'll send out the slides. I think I forgot to send out the slides today. So I'm going to do this, but I'm going to do it the way that I've always taught it, out of my head. I just need to do it on slides. So there's one step that we missed there that comes later in this little slide, little presentation that I will go through as well. So this will probably take us to the end of this session, and I'll record the rest by myself, or I'll make it part 2 of next week, and we'll go to 12 weeks for this seminar. So the question I use in the industrial synthesis of ammonia, so ammonia is NH3, N2 and H2 react to form NH3. This is called the Haber process, developed by a German chemist and basically brought the world out of food poverty. Ammonia, if you add nitrate onto that, it becomes ammonium nitrate, and it's used in fertilizer. The guy that created it was also a Nazi who created chemical weapons, but take the good with the bad. The question then goes on. In a typical reaction, 24 kilos of hydrogen and 84 kilos of nitrogen react to produce 68 kilos of ammonia. There's a limiting factor here, and that is one of these two will run out before the other one. And everybody says, well, it's obviously going to be hydrogen because there's only 24 kilos. And I hope this explains why we don't, if I was to balance the equation, I would do that, but don't have time to go through that. Everybody says, well, hydrogen's going to run out first because there's only 24 kilos. What we need to remember is that hydrogen is a 1.008 grams per mole. That's its mass. So it is very, very light. Nitrogen is 14.01 grams per mole. it is 14 times heavier, 13.8 times heavier than hydrogen. So, whilst the mass here of nitrogen is significantly more, there's going to be more moles of something. So more actual hydrogen, not how much it weighs, or more actual nitrogen, not in grams, but in moles. And we get this concept called the limiting reagent, or the limiting factor here, is going to be one of these two. And we can only figure that out when we convert this kilograms into moles, because the kilograms doesn't tell us much. We need to know how much of this is available to react, not how much it weighs. And then we'll find out from that that one of these will run out first. So, the atomic mass unit on the periodic table is in grams per mole. So we have to convert kilograms into grams. So let's do nitrogen first. $84,000 grams. And then we divide it in brackets by the molar mass of nitrogen, which we found on the periodic table. And we know that because of the balanced equation, that there's 2 nitrogen here. So we times that by 2, and that gives us, and what we do by dividing this here, is we get rid of the grams, and we're just left with the moles, or 3,000 moles. And this will make, I hope this makes more sense in the next step. So now we need to find out how much hydrogen there is. So we have 24,000 grams of hydrogen. And we need to divide that by the grams per mole. And by dividing, we get rid of grams. And it's also times 2 because it's H2. Now we have 11,900 moles. So we started with 84 kilos and 24 kilos. We started with 84 and 24, and it looked like there was heaps more nitrogen. But we need to know, so to put it another way, I'm not going to calculate this, but there is 3 of nitrogen atoms. So there is that number atoms. So we know that 1 atom of nitrogen reacts with 3 atoms of hydrogen to produce 2 of this. We don't care about the maths. We don't care how much it weighs. It doesn't tell us anything. We need to convert it into moles. And you can see that there's almost 4 times as much hydrogen. despite it weighing significantly less. And that's why we don't bother with grams or kilos. And now we need to determine which one will run out first. This balanced equation tells us that 1 nitrogen reacts with 3 hydrogen. So we need to times this by 3. And look at that. There's still more hydrogen available than there is nitrogen. So nitrogen is the limiting factor here. So now we know that nitrogen, when you mix this much nitrogen and this much hydrogen, and they start joining together, eventually the nitrogen will run out first, and the hydrogen will be there at the end by itself, and obviously with the ammonia as well. So we've got, that's how much we have of each. Now, remember that theoretical yield that we talked about? It's based on how much nitrogen there is. So now we get rid of hydrogen, it's irrelevant. We only need to know now, once we've discovered our limiting reagent, which is nitrogen, nothing else matters. So if we go back to our balanced equation, 1 nitrogen can produce 2 ammonia. So the stoichiometric ratio is 1 to 2. So 1 nitrogen, also 1 and 2, produces 2 ammonia. So we times 3,000 by 2. That is the theoretical mass, the theoretical yield in moles, but now we need to go back to kilograms. So we need to go back to kilograms because whilst in chemistry we don't really care about the mass, in industry where they're trying to sell this product, they need to know how much the mass is in kilos. So in order to do that, we do opposite of what we do. So we have NH3. So we need to know what the molecular mass of NH3 is. So that's nitrogen and hydrogen. Hydrogen is 1.008 times 3. 2, 4. And nitrogen is 14.01. Another way to do that is we take 6,000 and instead of dividing it, we times it by, so 6,000 times, which is the AMU of nitrogen, and then we add that to 3 times 1,008. And that gives us theoretical yield of 102,000 grams. Theoretically of 102,000 grams. So we've gone from start to finish, we haven't finished yet, but we've gone from grams to moles because we need to know how much of something there is or how many of there is, aside to how much it weighs. We've calculated that the nitrogen will run out first. And we calculated how much based on this ratio of 1 to 2. If there's no number here, then the number is 1. So 1 to 2. This is as complicated as this seminar series gets, if that is any consolation. and I will send out the on paper working out for this, which may be a little easier to follow. So 102,000 grams or 102 kilos. Now, our actual yield from the question is 68 kilograms. So 102, 68 gives us 67%. And again, I'll upload auxiliary videos of each of these steps, and I'll just focus on that individual step of going from. Actually, I might do that tonight whilst I'm talking to myself, actually. So, we now know the actual yield is 67%, so not great. In reality, this process should get you around 100%. I'm going to put that whiteboard away, and this week's videos will just be on that long-winded process to go from kilograms and then back to kilograms into a percentage. So I'm going to do, I might just power on through this. So that's stoichiometry. And is the bane of the existence of most chemistry students. And if I'm being honest, most chemistry teachers. So, talking about industrial chemistry, there's two main ones. That's not a very good term. It's two main chemicals that are produced. They're produced via the Haber process, and the contact process. And they're two most widely produced chemicals. So, Haber, he was also probably not the nicest person in the world. So, NH3 or ammonia is used to make fertilizer. It's made to used to make bombs. It's used to make lots of other things that my brain is not allowed me to access now. So, this is the Haber process that we talked about. So, you react nitrogen and hydrogen to produce ammonia. It effectively produces fertilizer from thin air. And this bit here, this delta means change in, H is heat. So change in heat equals minus 92 kilojoules per mole. That, if it's got a minus in front of it, it's what's called an exothermic reaction, or it releases heat. So when 1 nitrogen and 3 hydrogen bind together, they release 92 kilojoules of heat. And pointed to the equilibrium reaction, which means that the reaction will get to a point where so much product will be produced that it will actually start going backwards, and the product will be broken down into the reactants. Every system has a maximum amount of product that can be produced. When it gets to the product, when it gets to that amount, it will begin breaking down the product back into the reactants. So we can do this by changing the pressure, by changing the temperature, and we use these things called catalysts, and they are added to a reaction that's speeded up. So they're not actually involved in the reaction, and we can get the catalyst back. So we have this, I'm not even going to try and say the name because I have a few students who speak French and they laugh at me when I try to pronounce that. that once this equilibrium point is reached, the reaction will no longer take place. It will happen at the same rate going forwards to produce the product as it does going backwards to break down the product. What we can do is we can change the conditions so that the system will start producing more of the product or more of the reactants. It will shift to the right or shift to the left. So, we know that pressure is caused by gases bouncing off the side of a container. That's why when you put things under pressure, they bulge at the sides. They are being bombarded. So the more gas particles you have, the higher the pressure. On this side, we have 4 molecules of gas. So 1, 2, 3, 4. On this side, we only have 2. So if I increase the pressure in this reaction vessel, what happens is, because there's less gas molecules on this side, the system will go, I don't like that very much. And it will begin producing this because it reduces the amount of gas in that box. And eventually the pressure goes back to normal and the equilibrium is then balanced again and everyone's happy. So the right-hand side has less particles. So if it starts producing this from this, the pressure will come back down. So temperature. Remember I said it's exothermic. So every time nitrogen reacts with hydrogen to produce ammonia, heat is released. So if I bring the temperature down, the system is going to go, hang on, I want to bring that temperature back up. So it will react nitrogen and hydrogen to produce the product, because every time it does that, heat is released. And as we increase the heat, the system goes back to equilibrium and everyone's happy. So if I decrease the temperature, it will produce more of the product, because when it does that, it releases heat, which brings the temperature of the box or the vessel back up. So the equilibrium will shift to the right to increase the pressure. Sorry, increase the temperature. So this is where science and realism collide. We want to, if we increase the pressure, then we get more of the product. So why don't we just increase the pressure, the temperature? Sorry. Why don't we increase the pressure to 1 trillion atmospheres? And why don't we just make the temperature minus 200? They're the best condition. And obviously, a little bit of common sense needs to come in. I can't remember the exact figure, but to keep something at 1 atmosphere of pressure, so for 2 atmosphere of pressure for a long period of time, which is twice the pressure that you feel now, is very, very expensive. And if we look at this based on what we just learned, then we should just be able to increase the pressure and decrease the temperature, and we'll get loads and loads more. Every reaction has a limit to how much can be produced. So we use this principle to manipulate those conditions to make sure that that limit is increased. So lower temperatures and high pressures. So at 200 degrees and 1,000 times atmospheric pressure, we get almost 1 + 1 = 2. 1,000 atmospheres of pressure can't really happen on an industrial scale. It might happen in the lab, but very, very difficult to achieve. And if you do have 1,000 atmospheres of pressure and it goes bang, you would take out a town. So there has to be some safety factors come in, which is boring. Scientists hate safety. Let's just crank everything up and get the most out of it. Or maybe that's just me. So we have these catalysts. And they just help the reaction get to that endpoint faster. So when we're dropping the temperature, we're allowing for theoretically more ammonia to be produced, but the reaction of producing ammonia will slow down. So we add these catalysts to increase the rate of reaction. Changing the conditions will mean that theoretically we can get more, but if we drop the temperature too much, it takes too long to get to that. So we add these catalysts and they speed up the rate of reaction, but they don't actually take part. So you put this iron oxide in, and at the end, you take it out. So magnetite, ferrous, so. And it goes in, it speeds up the reaction or it lowers the activation energy required, allowing us to drop the temperature without making the reaction so slow that although we can produce 20% more, it takes a year longer to get to that point. So there's no point in doing that. So that's why we use catalyst. So balancing conditions. We have to have a balance of temperature and pressure. We can't just exponentially increase the pressure and lower the temperature. In reality, it doesn't work. So 350 to 550 and 100 to 200 atmospheres of pressure. And when we use a catalyst, it gives us roughly the same results as if we had, I think it was 200 degrees and 1,000 atmospheres of pressure. So we have to balance cost, practicality, and safety to achieve the most advantageous results. Okay, this can be a long, we've got about 10 minutes to go, I think. Sulfuric acid, everyone knows sulfuric acid, it's in your stomach. And so we produce 231 million tons of it every year. So 231 billion liters. Most of the pharmaceutical drugs you take are attached to hydrochloric acid, or HCl molecule. Batteries, dyes, pigments, fertilizers, they all contain sulfuric acid. And we make it using this contact process. And it contains multiple steps, but what we call this reversible reaction, or the reaction that eventually reaches that point where the equilibrium makes the reaction go forward at the same rate as it's going backwards, so no more product is being produced. So this one we're not really looking at, but this one, if you see this, this is a reversible reaction. So the reaction, once it reaches a certain point of dynamic equilibrium, the sulfur dioxide and oxygen are reacting to produce 2SO3 as quickly as 2SO3 is breaking up back into these. So it's hit the theoretical maximum of how much sulfuric acid it can hold, so it begins to break it down to balance that out. And when it does that, we've got a minus figure here, so change in heat. So we know that heat is released. So same principles as before. We have an exothermic reaction producing heat. When these two are mixed together and they become this much heat is released because it's a minus. If that was a positive number, that will be absorbing heat. So if we increase the pressure, there's less molecules on the right. So the equilibrium will begin creating more of this, because there's only 2 gas particles, whereas here there's 3. If we decrease the temperature, the same reasoning applies. So we have to balance the condition. Yeah, so we have to balance the safety and practicality against everything else. So increase the pressure, the effect on the total amount of product that can be made increases with decreasing temperature, increases with increasing pressure. And the reaction rate increases as well. So the speed at which the reaction happens. So there's 2 parts. You have the speed at which the reaction happens, so how quickly that reaction is going, and then you have the theoretical maximum of how much can be produced inside a particular vessel. I got through that quicker than I thought. I'll probably do lots of videos for this week. This is probably the most complicated one. So thank you for coming, and I will see you, both of you, before this next week.